Hi, my name is Sujit Kumar, and I'm a PhD student in Control and Automation Group. My thesis topic is still the integrity attack against cyber physical systems, its design and countermeasures. So, the flow of this presentation will go like this. Uh, the content of the slides are: first, I'll discuss the cyber physical system model considered in the work, and what is the different type of attacks that can take place in the context of cyber physical systems, and what could be a possible solution against such attack. So we propose an attack aware resilient control architecture for cyber physical systems, and we discuss some work done during this semester and work under progress. So the cyber physical system this represents a rich class of system in practice, ranging from infrastructure systems and like power plant, transportation networks, all that. So cyber physical system is a class of system where uh, the physical systems are controlled via cyber elements or cyber components through communication of some control variables. So we consider here a distance plant operator setup. So plant and controller are non-collocated setup. That is, plant and observer are situated at far places, and the control action is taken from the estimated variables shared through communication channel. So these setups make the system vulnerable to manipulation of these shared signals via open network. So here in this figure, we can see that the plant is affected under usual disturbances, that plant noise and measurement noise. And this is a general setup. So in particular, we study a linear plan and observer, a Leonberger type observer, and a detector is a baseline detection mechanism that computes a residual signal and compares with a threshold value, and decides whether there is an anomaly present in the network system or not. So, after this introduction of the networked cyber physical system, so there are various attacks reported in the literature and media in the past 10 or 15 years. And from system theoretic perspectives, those class of attacks can be classified into two main types: denial of service attack. So what attacker does, that so availability of data is compromised. For example, in the previous slides, we see that the networked cyber physical system. So the control and the operation of the plant depends upon the uh, output and control input generated data, that those signals are shared via communication channel. So a denial of service attack can be achieved by jamming the communication channel. Other second class of attack is the integrity or deception attack. So the shared signal, that where the integrity of that information, that shared signal is compromised, then it falls under the category of integrity or deception attack. So it is usually done by injecting false data in the communication network or manipulating some cyber component such that false data are generated or injected into the system. So mainly three class of the deception or integrity attacks has been studied in the or reported in the literature. One is zero dynamics attack, other is covert attack or steal the integrity attack, and a replay attack. There are other class of attacks like switching attacks and all, but detectability or other properties mm, that are very difficult to analyze for those class of attacks. So here in this work, we consider covert attack or stealthy integrity attacks. So covert attack, stealthy integrity attacks are basically false data injection attacks, and it is done in coordinated way that uh, whatever attack signal is injected into the actuator channel, the effect of that injection is compensated by some mechanism in the output measurement so that the output measurement based detection mechanism cannot detect it. So this is the mathematical model of the plant on observer. So this is x dot is equal to x plus bu bar plus omega p and omega m. Process and measurement disturbances are there, and it's a very simple Allen-Berger observer. U bar and Y bar are the compromised signals on actuator communication channel and measurement communication channel. U bar is the actual control signal received at the plant, and Y is the plant output. These are the signals there. And the baseline detection algorithm is based on the computation of output residual. So residual is computed based on the available measurement and the estimated output computed by the Leinberger observer. And this is the decision logic that some norm-based residual calculation is done. So if that norm is less than some threshold, then there is a normal operation. And if it is greater than, so then that one an attack is reported. So at this point, we can define what is a stealthy attack. So an attack is said to be stealthy if the residual detector fails to detect its presence. That is, an attack signal is generated such that it satisfies this condition and still, harm the operation of the system. In addition, the attack signal is said to be perfectly stealthy if it is stealthy with ZA of t is equal to 0. What is ZA of t? So ZA of t is the impact of attack on the residual signal. So this signal will be defined in next few slides. So what problem basically there are the two class of problems will be studied under the framework of still the attack generation and the counter designing countermeasures against that. So first problem is for a given CPS, identify an attack model first. And second would be devise an attack aware resilient control architecture, which has following desired features. So what we mean when we say attack aware resilient control architecture. So this architecture will comprise of an enhanced detection mechanism that can detect the stealthy attacks. And resilient control means that the mitigation of attack is also provided by some additional component or something like that. So this will have following two desired features that enhance the detection mechanism such that attack is detected and redesign the control input such that the impact of attack is mitigated. So we study here like for the when for the simple case to just get the idea of the framework. So we consider disturbances, zero disturbances, and we assume that the attacker has complete model knowledge. That is AA that is equal to A, and we consider a linear attack model that and given that the attacker has real-time measurement of the system. So this attack model can generate and steal the attack. So there could be two cases based on the available measurement. So one is H is equal to 0. So it is basically an open loop attack, simply a bad data attack. And the second is H not equal to 0. So there is output is used in feedback to for the attacker's dynamical system. So attacker can make the plan to follow a desired behavior or even destabilize the plan. So how to analyze stealthiness of attack? So the um, basic framework to analyze stealthiness of attack is to consider the system under the effect of attack and the nominal system. So since this is a linear system, so state can be represented as sum of the effects due to those two inputs, that nominal input and the attack input. So here we represent xn represents the nominal state of the system. Nominal model of cyber physical system can be written as xn dot is equal to axn plus bu and yn is equal to cxn, and xn hat is the nominal Leuenberger observer. And residual signal for the nominal case is defined as yn minus yn hat. So to analyze the stealthiness of attack and to ensure that this model will achieve stealthiness, so we define error vectors, that error of the state evolution between under attack system and the nominal system, and the error between the state estimates of under attack system and the nominal system, and the differences of residuals. So we can see that if XA is generated such that ZA of t is 0, then the residual signal under attack is equal to the normal residual signal. That is, the perfect stealthiness can be achieved. So in next few slides, we'll see that this can be done. So mm, the closed loop dynamic system, like the dynamic model of the cyber physical system, can be written as, and if we define a new variable, that w is equal to ea minus ea hat minus xa, and when we take a derivative of this and with after some algebraic manipulation, we find that w dot is equal to a minus lc w. And by design of the cyber physical system, the Leuenberger observed design, a minus lc is a Hurwitz matrix. So at t tends to infinity, w goes to 0. So w goes to 0, that ensures that ZAT goes to 0, which ensures that the attack is perfectly stealthy. So the next question is how to enhance the Leuenberger observer-based detection mechanism, or the baseline detection mechanism, such that we achieve attack-aware resilient cyber physical system. So to do that, so there are like few options. So first we have to understand that what what was the basis of stealthiness for the attack. So attacker has complete model knowledge of the system, at least the system matrix. So uh, the one way is that we devise some mechanism such that attacker cannot identify the model, or the model of the attacker is different from the actual model. So it can be done by putting some uh, input modulation filter in the plant side and the uh, controller side. So the attack awareness is achieved by introducing that input modulation filter, and that input modulation filter is driven by some dynamic signal. So what could be that dynamic signal? So there are few options. For example, in some papers, a periodic signal has been used for as dynamical signal, such that the attacker cannot get the exact signal what is shared on the network. But after some recording, periodic signal has a deterministic behavior. So the period of the signal and the amplitude of the signal can be computed by the attacker for if they can eavesdrop for a sufficient amount of time. So chaotic signals presents a viable solution for that. So this attack aware control architecture, uh, it constitutes of an input modulation filter which depends upon a dynamical signal, and that signal is generated by chaotic circuits which are in master slave configuration in the plant side and the observer side. So in the next slides we see that how this achieves attack awareness and how it mitigates the effect of attack. Or can we do that? So the attack-aware resilient CPS architecture is composed of a physical plant. So we write it as AX plus. Now the existing architecture has been modified. So the input is modulated by some function GP of eta. So this is input modulation function. Y is equal to CA, y, U bar is equal to A. And eta is the dynamical decoding signal generated by the master chaotic circuit and observer-based state feedback control designed as this. So how eta and eta hat are generated. So the input modulation filter we like take as a low pass filter kind of thing. So integrated 1 upon 1 plus epsilon eta, and in the observer side 1 upon 1 plus epsilon eta. So with input modulation filter, the closed loop dynamics of the state evolution and the error dynamics can be represented by 1. And we take a Chua circuit for the dynamical signal generation, which has standard equations, and results are available for synchronization, output-based synchronization for these two circuits in master-slave configuration. So next, the goal of developing attack-aware resilient control architecture is that if we incorporate something additional to the existing system, then the nominal performance should not be disturbed in the in the absence of attack. So we study impact of incorporating dynamical signal and input modulation filter into CPS configuration. So a standard result with based on Lyapunov analysis. So if you consider the system 1, which dynamic signal eta and eta hat is given by 2 and 3, then system had these two following properties. So global stability and exponential convergence is guaranteed when UA 0 and UYA is equal to 0. So that is when there is no attack, the stability is preserved. And when there are attacks, so the results are in the input to state stability sense. So under the presence of attack, the attack aware resilient control architecture ensures input to state stability, which in some sense is provides resilience against such attack. And how does it detect that and the presence of attack? So for that, we again analyze that W variable, uh, which defines the residual signal. So xn dot and xn hat dot under the with the input modulation filter, then W dot can be written as, which is a linear system with some additional term that can be simply written as the solution of state equations. And we see that this ZAT will be 0 only when UA is 0. So if UA is non-zero, then this mechanism uh, gives non-zero residual signal, and this attack can be detected. So for the validation of these results, a benchmark system, quadruple tank system is considered for assimilation purposes, where A, B, and C matrix are given. K, L, and K are calculated based on Lyapunov design methods. And this is the plant state X under attack without input modulation filter. So we see that at time 400 seconds, the attack start. I mean, after it is settled to 0, the plant is stabilized. There is attack, and every state goes to a different final value. And we see that the residual signal without input modulation filter, then there is no spike or any change in the residual signal performance. And we see the next, this residual signal in attack-aware resilient controls, that that impact of that dynamic signal. So this residual signal is shows some spikes. So the attack can be detected. So this was the basic framework for attack-aware resilient control architecture based on input modulation and uh, incorporating nonlinear chaotic signal in the control architecture. So we study in the attack aware resilient control against an attacker with. We also study the stealthiness of attack when the attacker doesn't have complete model knowledge. That attacker's system matrix is not equal to uh, the actual system matrix. Then we derive some bound on the model knowledge difference and relate it to the detection threshold of the detection mechanism. Investigation of attack aware region against destabilizing. This is very important. So the attacker had two choices, whether it can use the real-time measurement of the system or it cannot. So like it does not uses that. So for h is equal to 0, the attack is just a bad data attack. And for h not equal to 0, there are few possibilities. So if attack h is not equal to 0, then the attacker can manipulate or it can make the plant follow some desired behavior. Also, with the judicious choices of h, the attacker can destabilize the plant. So it will be an interesting avenue like to investigate that how this existing architecture can be appended with some additional component such that it is resilient against destabilizing attack. So we are investigating that competitive interaction based dynamic feedback control such that this architecture is resilient against some destabilizing attack. And so this is the result, like the bound on attacker's model knowledge difference. That is simply computed based on the difference between the model knowledge and we use differential inequality to achieve this bound. Next, the ongoing work is so for the linear systems, the linear attacker model achieves stillness. So we are investigating what for a particular class of nonlinear cyber physical system where there is a lipstick nonlinearity, and we are investigating following two questions: stillness of attack for nonlinear cyber physical system with respect to an given anomaly detector, and attack aware resilient control architecture designed for nonlinear cyber physical system. Some initial results are there, and we are like planning to validate on physical system on quadruple tank system. That's it from my side. uh, I'll thank you.